Welcome to the next session. Now in this session, we continue classroom workbook followed by a new concept Laurent series followed by types of singular points and residues of complex valued functions. Right? Now let us start the session with question number 18. Go through classroom workbook. Question number 18. If f of z equal to x square plus ay square plus I into bxy is a complex analytic function of a complex variable z equal to x plus iy. It is given that the function is analytic, where I equal to square root of minus 1. Then what are the values of a and b? Options are given. Now it is an analytic function. When something is an analytic function, implies it is differentiable. If something is differentiable, CR equations must be satisfied. CR equations must be satisfied. Now let us see. Here f of z is in the form u of x comma y plus I into v of x comma y. What is u of x comma y? X square plus ay square. And the value of v is bxy. So let us apply CR equations. First CR equation is ux equal to vy. Ux means dou u by dou x. Vy means dou v by dou y. This implies dou u by dou x equal to 2x. Dou v by dou y equal to bx. You can cancel x on both sides. So therefore the value of b is 2. There are three different options with b value 2. In option B, C and D, b values are 2. So you need to find a also. So we got the value for b by using first CR equation. Ux equal to vy. Dou u by dou x equal to dou v by dou y. What is dou u by dou x? 2x. Dou v by dou y is bx. Cancel x on both sides, you get b value 2. Now apply second CR equation. The second CR equation is uy equal to minus vx. What is uy? Dou u by dou y. Vx minus vx means dou v by dou x. This implies dou u by dou y is 2ay. Dou v by dou x, v is this, so dou v by dou x is by. Dou v by dou x is by. This implies y will be cancelled, so 2a equal to b. But a equal to b by 2. So b value is 2, therefore a value is 1. So when you apply second CR equation, we were getting a value 1, and anyhow by using first CR equation, b value 2. Therefore option C is right answer. Next question number 19. If f of z equal to iz plus k into real part of z plus I into Im of z satisfies CR equations, then what is k value? So directly f of z is given. So inside f of z, k is given. We need to find k is some constant. We need to find k, for which if this function satisfies CR equations. Now whenever it satisfies CR equations, you can use any one of the equation. So like this, you can use either equation 1 or equation 2. Now let us simplify this function at first, because this is not in the form u of x comma y plus I into v of x comma y. Here z is a complex variable, so z is nothing but x plus iy. So f of z equal to I into x plus iy plus k into, what is the real part of z? X. I plus I into imaginary part of z is y. So therefore this is ix, I into I square minus y plus kx plus iy. So therefore this is kx minus y plus I into x plus y. Now this is in the form u of x comma y plus I into v of x comma y. So since it satisfies CR equations, ux must be equal to vy. Let us use the first CR equation. If I don't get k value, let us apply second CR equation. What is ux? Here basically u is nothing but this kx minus y. V is nothing but x plus y. So therefore in this case, ux means dou u by dou x. So dou u by dou x equal to dou v by dou y. What is dou u by dou x? K. Dou v by dou y is 1. Therefore, the value of k is 1. Directly, if you write this function in the form of u of x comma y plus I into v of x comma y and apply CR equations, you will get k value 1. Only thing is you need to express this function in the form u of x comma y plus I into v of x comma y, and then you use any one of the CR equation, you will get k value. Here z is x plus iy. So real part is x. Imaginary part is I. So this is I into x plus iy plus kx plus iy. Simplify this, this becomes ix minus y plus kx plus iy. So therefore, you can take this is kx minus y plus I into x plus y. This is u value, this is v value. Apply CR equation, we were getting k value 1. Next question number 20. If f of z equal to u of x comma y plus I into v of x comma y is an analytic function of a complex variable z equal to x plus iy, where I equal to square root of minus 1, u of x comma y equal to 2xy, then v of x comma y may be expressed as. So earlier we had a discussion about Cauchy-Riemann equations. It is in the form u of x comma y plus I into v of x comma y. It is given as an analytic function. U is given as 2xy. Then what can be value of v in terms of x and y? Let us see options. Option A is minus x square plus y square plus k. Option B is x square minus y square plus k. Now when you go through option C, this is x square plus y square plus k. Option D, this is a minus x square minus y square plus k. Now let us get the value of v in terms of x and y using CR equations, or at first I can do this by verification of options. Let us verify options. Now this is analytic implies CR equations must be held. So what is ux? Ux equal to 2y. So therefore Vx must also be equal to 2y. This is very clear. What is second CR equation? Uy equal to minus Vx. But what is Uy? Uy is 2x. So therefore minus Vx must be equal to 2x. Minus Vx must be equal to 2x. So Uy must be equal to minus 2x. What does it mean? This means that Vx equal to minus 2x. So in the first CR equation, values must be exactly same. Ux is 2y. So therefore this is Vy actually. This is Vy. So Ux must be equal to Vy. Vy is 2y. Uy must be equal to minus Vx. Therefore this must be Vx equal to minus 2x. In case of second CR equation, minus symbol must come extra. But in case of first CR, both must match exactly. Now let us verify options. Suppose if this is V. Suppose if this is the expression for V, for example, then what must be Vy? This is 2y. What is Vx? In this case, minus 2x. So therefore, first option A fulfills Vy equal to 2y, Vx equal to minus 2x. So it may be right answer, may not be right answer. Don't confirm and don't eliminate this. Now come to B. Suppose if this is V, then what is Vy in this case? Minus 2y. But according to first CR equation, Ux and Vy must be equal. So Vy must be 2y. But in case of second option, Vy is minus 2y. So first CR equation failed. So when it failed, you can eliminate this option. Right? Now come to C. Suppose if it is V. Now you can see here Vy is 2y. So it verified. So go for Vx. In this case, Vx is 2x. But Vx must be minus 2x. Vx must be equal to minus 2x. So it failed first CR equation if it is V. So eliminate C. Now here suppose if it is V. Now in this case Vy equal to minus 2y. But according to first CR equation, Vy must be equal to 2y. Therefore it failed first CR equation. It is wrong option. Therefore CR equations are not satisfied by option B, option C and option D. So ultimately A is right answer. So this is by verification of options. Do this. Now this can be handled by using CR equations indirectly rather than verification of options. Now let us see this. So here what is ux? Ux is 2y. So vy must be equal to 2y. Uy equal to 2x. So vx must be equal to minus 2x. Now when you look at the first CR equation, the first CR equation is ux equal to vy, right? So ux values and vy values must be equal, but I want v value. So what is ux? 2y. So vy equal to 2y, but vy means dou v by dou y. This is 2y. So in this case, dou v by dou y equal to 2y. So this implies dou v equal to 2y times dou y. Now v variables are one side, y variables are one side. Apply integration on both sides, you will get v equal to y square plus some constant k. Y square plus some constant k. So this I call it as v1 expression. Now let us take second CR equation. The second CR equation is ui equal to minus vx. So therefore vx equal to minus ui. What is ui? Ui is 2x. That means vx equal to minus 2x. So vx means dou v by dou x. This is minus 2x. Dou v equal to minus 2x into dou x. Now v variables are one side, x variables are one side. So solve this, you will get v equal to minus x square plus some constant k. But here I call it as v2. So already v1, v2. So in both the expressions, constant k is common. Instead of taking 2k's, you can take 1k. So therefore the value of v is v1 plus v2. If a quantity repeats multiple times, you consider only one time. So from the first CR equation, we were getting v1 is y square plus k. From second CR equation, we were getting v2 equal to minus x square plus k. So therefore, in this case, you will get v1 plus v2 as v. So this is minus x square plus y square plus k. So therefore, this is the way to get v value. Because if options are given, then you do it by directly. If options are not given, they may ask question in the different manner like this. This is the function. U is given like this. If this function is analytic, then what is v of 1 comma 2? They may ask you like this. What is v of 1 comma 2? In that case, you need to find v value. Of course, even you need not write the constant k. So in that case, if v is a minus x square plus y square, you need to find what is v of 1 comma 2. So x is 1, y is 2. So when the questions were given like this procedure gives best result. This is the only way. This is the only way. Suppose if options are given, you can do by previous method or by this method. Okay. So even work out this also. Next question 21. An analytic function of a complex variable z equal to x plus iy is expressed as f of z equal to u of x comma y plus I into v of x comma y, where I equal to square root of minus 1 and u equal to x square minus y square. Then the expression for v should be, this is just like previous question. Now let us see what are the options. Option A is xy plus k. Option B is 2xy plus k. Option C, xy minus k. Option D, x square y square plus k. So it is exactly our previous question. Now you can verify CR equations. Here what is ux value? Ux value is 2x. So therefore Vy must be equal to 2x. But when you look at option A, suppose if you assume that this is V, in this case Vy equal to x, but Vy must be 2x. But in case of option A, we were getting Vy value x. So option A does not satisfy CR equation, eliminate option A. Now come to B, if it is V, now in this case, what is Vy? Vy is 2x. So it satisfies first CR equation. So go for second CR equation. So for second CR equation, Uy is required. This is minus 2y. So therefore Vx should be minus of this. It must be 2y. In this case, Vx is 2y. Therefore second option satisfies both the CR equations. When an option does not satisfy any one of the CR equations, eliminate that. But if it satisfies both the CR equations, it may or may not be right answer. So don't confirm and don't eliminate also, right? I repeat the points. If an option does not satisfy any one of the CR equation, eliminate it. 100% wrong answer. So that is called elimination technique method. But if an option satisfies both the CR equations, it may be correct choice for V or it may not be correct choice for V. In that case, we need to go for another analysis. So in that case, you don't confirm and don't eliminate also. So I am putting V in the hold position. Now when you go to option C, so therefore in this case, Vy equal to, this is x only, but Vy must be 2x, so it fails, eliminate C. So here in case if it is V, so in this case Vy is, for example, this is 2x square y. So Vy must be 2x. Therefore option D also does not satisfy the first CR equation. So option A, C and D does not satisfy the CR equations. Therefore option B is the right answer. Now with this we have finished classroom workbook questions from 1 to 21 based on the basics of complex variables, CR equations, singular points, yes or no, and even bilinear transformation. Now we move to the next concept of complex variables, that is a Laurent series. Suppose we have a function f of z having z0 as a singular point. Here z0 is a singular point of the complex valued function f of z. So singular point means this function has no derivative at the point z0. That means this function can be expressed in the series form like this. So here f of z can be expressed in the form sigma n equal to 1 to infinity a n divided by z minus z0 whole power n. Summation n equal to 1 to infinity. So you can take n values 1, 2, 3 and so on. That means you have infinitely many terms. That's why this is called a Laurent series expansion of f of z about z equal to z0. This is called Laurent series expansion of f of z about z equal to z0. Let me expand this. So summation means additions. So take n value 1, you will get a1 by z minus z0. N value 2, a2 by z minus z0 whole square. Next n value 3, a3 by z minus z0 whole cube, plus and so on. So we have infinitely many terms, and here a0 comma a1 comma a2 and so on an. All these are some constant values. All these are constant values. In that case, this is called the Laurent series expansion of f of z about z equal to z0. Now, so there is one important point in case of all these constants is, suppose if a0 is 0, if this constant is 0, a1 is 0, a2 is 0 and so on. If all constants are 0, then I will get f of 0 equal to 0. Constant function. Constant functions will not have any singular points. Therefore, the condition among all these constants is, all these constants are constants, but out of these constants at least one constant should be not equal to 0, right? I told you what happens if all constants are 0. If a1, a2, an and so on, all these constants are 0, then my function f of z becomes constant function 0. Constant functions will not have any singular points, but I am saying that z0 is one of its singular point. Okay. Therefore, whenever I have a series expansion for f of z like this, then this is called a Laurent series expansion of f of z about z equal to z0. Let me tell you one example. Suppose I have a function f of z equal to, for example, 1 by z minus 2. Now this I can write it as 1 by z minus 2 plus 0 by z minus 2 whole square plus 0 by z minus 2 whole cube plus and so on. Therefore, this is called the Laurent series expansion of f of z about z equal to 2. The Laurent series expansion of f of z about z equal to 2. Because z minus 2 is written in the denominator, so that's why 2 is called a singular point of this function. Okay. So write the definition at first. Let f of z be any complex valued function. Let f of z be any complex valued function and z0 be one of its singular points. Let f of z be any complex valued function and z0 be one of its singular points. Then f of z can be represented as, f of z equal to sigma n equal to 1 to infinity an by z minus z0 whole power n. That is equal to a1 by z minus z0 plus a2 by z minus z0 whole square plus a3 by z minus z0 whole cube plus and so on. Where a0 comma a1 comma a2 and so on are constants, where a0, of course we started from 1 onwards, so a1 only, a0 should not be there. where a1, a2 and so on, an and so on are constants such that at least one of these constants is not equal to 0. This term is very important. Such that at least one of these constants is not equal to 0. Is not equal to 0. And this is called the Laurent series expansion of f of z. And this is called the Laurent series expansion of f of z about z equal to z naught. The Laurent series expansion of f of z about z equal to z naught. Write this example. Now we discuss three basic examples of Laurent series expansions. They are sin z, cos z and e power z. We have seen the series expansions of sin x, cos x and e power x. They are called Taylor series expansions and they will be turned to Laurent series expansions in case of complex variables. Let me tell you what are the series expansions of sin z, cos z and e power z. So let us start with sin z. The series expansion of sin z is z minus z cube divided by 3 factorial plus z power 5 by 5 factorial minus z power 7 by 7 factorial plus and so on. This is not a new thing for us. We have seen sin x series expansion during differential calculus chapter 3. In place of x we have a complex variable z. Similarly, the series expansion of cos z, this is 1 minus z square by 2 factorial plus z power 4 by 4 factorial minus z power 6 by 6 factorial plus and so on. Now the last example we need to discuss is e power z. So its series expansion is 1 plus z by 1 factorial plus z square by 2 factorial plus z cube by 3 factorial plus and so on. Therefore, these three are Laurent series expansions of sin z, cos z and e power z. Note all these points. Next concept, types of singular points. We have three types of singular points. Let me discuss one by one. The first category is removable singular point. Shortly we call it as RSP. Removable singular point. Let us see. Suppose we have a complex valued function f of z and z0 is one of its singular points. We say that this is a removable singular point of f of z if the Laurent series expansion of f of z about z equal to z0 has no terms of the form 1 by z minus z0. So whenever this happens, we say that z0 is a removable singular point of this function. Just since I am saying that it is a singular point, z minus z0 terms must be there at least one time in the denominator part. If I don't have z minus z0 in the denominator part, then I can't say that z0 is a singular point. Yes or no? Suppose if I have an example like this, 1 by z minus 1. Now 1 is one of its singular point. Suppose if I have like this, still I can say that 1 is one of its singular point. But here 2 is not a singular point because there are no z minus 2 terms in the denominator. 3 is not a singular point of this function because z minus 2 terms are not available at the denominator level. Yes or no? Therefore, if z minus z0 terms are there at least once in the denominator, then it is called a singular point. But I am saying that it is a removable singular point. That is possible when you go for series expansion, that the denominator z minus z0 terms will be cancelled out with the numerator part of z minus z0. So if the Laurent series expansion of f of z about z equal to z0 has no terms of the form 1 by z minus z0, then this is called a removable singular point of this function. See, no terms, that means singularity can be neglected by going for series expansion. That's why it is removable. Basically, it is a singular point. Singular point means it's a drawback of a function, but its a drawback can be removable. Its a drawback can be removable by going for series expansion of f of z. That's why it is called a removable singular point. Let me tell you one example. Suppose f of z equal to the functions z minus sin z divided by z cube. Now in the denominator we have z minus 0 whole cube. This is z cube, I can write it as z minus 0 whole cube. Yes or no? So therefore z minus z0 terms are there in the denominator. So 0 is one of its singular points. So 0 is a singular point of f of z. But its singularity can be neglected by going for series expansion of this. Let us see, this is 1 by z cube into z minus, the series expansion of sin z is z minus z cube by 3 factorial plus z power 5 by 5 factorial minus z power 7 by 7 factorial plus and so on. Now this z and z will be cancelled, so it is 1 by z cube into z cube by 3 factorial minus z power 5 by 5 factorial plus z power 7 by 7 factorial minus and so on. Now you multiply with 1 by z cube, this expression becomes 1 by 3 factorial minus z square by 5 factorial plus z power 4 by 7 factorial minus and so on. Now therefore the series expansion has been simplified. Interestingly, there are no 1 by z minus 0 terms here. In the series expansion, 1 by z minus 0 is not there. Therefore, singularity can be removed by going for series expansion of this function. Therefore, here 0 is a singular point. But when you gone through series expansion of this, 1 by z terms have been eliminated, have been removed. That's why 0 is a removable singular point of this function. Write the definition. Let z not be a singular point of a function f of z. Let z not be a singular point of a function f of z. We say that z naught is a RSP of f of z we say that Z naught is a RSP. RSP means removable singular point. We say that Z naught is a RSP of f of z if the Laurent series expansion of f of z, if the Laurent series expansion of f of z has no terms of the form 1 by z minus z naught. If the Laurent series expansion of f of z has no terms of the form 1 by z minus z naught. Write this example. At this moment, you write this as, here 0 is a singular point of f of z. 0 is a singular point of f of z. And then write these series expansions. Finally, write this. And at this moment, you write like this. The series expansion has no terms of the form 1 by z minus 0. The series expansion has no terms of the form 1 by z minus 0. Therefore, 0 is a RSP of z minus sin z by z cube. 0 is a RSP of z minus sin z by z cube. Thank you so much. The session is over. In the next session, we can go for pole and essential singular points followed by residues.